Okay. So now we're talking about this particular compound reacting with this, that is methanol. So now in this particular reaction, so we try to split this in order to get, we disconnect this in order to get a negatively charged atom and a positively charged atom. So now this is based on our knowledge from carbon ions, our Haddock condensation, the cross Haddock condensation, the Clancy condensation. You should have an understanding about this. So now the first thing we do is that we punch this button with this ion. So then, which causes the delocalization of pi bond. So the pi bond dey migrate and attach to oxygen, allowing oxygen to have a what? To carry a what? A minus charge. That is, the minus charge indicates due to the presence of excess electrons. So now, allowing oxygen to carry a negative charge, which indicates the presence of what? Excess what? Electrons. So now, when there is excess electrons, we then this element comes in. So when there is excess electron, so this one comes in, pushing out this chlorine atom. We can see here, so it has pushed out this chlorine atom as there is a migration of electrons here. So then there is also a migration that is cutting off these chlorine molecules, as you have seen it here. So don't forget, this is what actually happens here in this scenario. This is what happens. We have O minus, then this chlorine molecule is being cut off. We have OCH3. We have OCH3. Then after this OCH3, we introduce our H plus. We can introduce water into the equation. Where we split water, where we split water molecules, we have H plus and OH minus. So then this H plus is attached to this. So we can have H plus here. We have O minus and H plus. So then they act together. So there's a reaction together. We have O. So we have for example, we have O minus. We don't even need the introduction of water. Since we have O minus, so this double bond can go back to these excess electrons can go back to right to time. So that is, these excess electrons can move back here. So then, since we've eliminated the excess electrons, so there's also a formation of double bond again when we add our reagent. So the double bond is back to place and the negative charge is what? Eliminated. So we have this what? Compound. So now, you all know that this is a forward reaction. That is, this is the starting material to give us what? This in a normal chemistry reaction. But now you can be asked, that is, find the electrosynthetic reaction of this what? Particular what? Compound. So now we have it here. This is our what? Our target molecule. When we talk about target molecule, that is, which molecules have the molecules we are discussing now, that is the molecules that we are trying to find their possible smaller units. When we talk about finding what? Possible what? Smaller units. So likewise, when we talk about polymers, we can have very, very big complex polymers that contains of thousands of what? Monomers. So now we can different polymers, for instance, like Linon C6, likes of hexamethylene diamine, Linon C6 that is being used in our normal nylon. So that is, and adipic acid. That is, those compounds finding their possible monomer, that is the smaller structures, the starting material. For example, we can be told what is the monomeric unit of Linon C6. So we should know that this and this react together to give us line of 6,6. So likewise this, we have this compound which is a target molecule. We are now asked, that is, what can make up this compound? What makes up what this compound? So now the first thing we have here is our what? Is our retrosynthetic arrow. So we can see. So this already indicate that this is a retrosynthesis reaction with this arrow, which has an open end space. So you can see we eventually have our starting material, which is this and this. So these are the precursors. Very simple. If you already know the reaction mechanism of a particular reaction, the reverse is just something easy. It's like you embark on a journey. You are moving from Lokoja to Kano. Then you should be able to, when you get to Kano from Lokoja, you should be able to find your way back to what? Lokoja, because that's the same route you passed. So you embarking on a journey, then you should know the way back. That is, you are coming from a particular location, then going back to that location shouldn't be what? Hard. It should be definitely easy. So the first step in retrosynthesis is to what? Is to know the forward reaction first. Is to know what? The forward reaction. Like this is a case example. This is the forward reaction for this. That going backwards shouldn't be easy, shouldn't be difficult. That is, we have it here, our target molecules. So going backward should be what? Very easy, because you've already journeyed forward. So going backward should be what? Easy, should be difficult. So the first thing I would advise you is that what? Work on your forward reaction first before you can embark on the what? On the retrosynthesis, that is the backward reaction. So now we're talking about the second terminology here is we talk about disconnection. Let's say it is an analytical break. Let's say an analytical operation which breaks a bond and converts the molecules to a possible starting material. It is a reverse of chemical reaction. When we're talking about disconnection can simply mean bond cleavage. That is the breakdown of bonds. For example, you have A and B attached to a bond. So that is, how can we A and B attached to a bond? That is, you want to disconnect them into two separate things. Hypothetically speaking, A and B connected with a bond, that is, we want to disconnect both into two distinct molecules. So for example, we have A and B. So the next thing is what? To disconnect. How do we disconnect? That is, we break down the bonds, or we can also call bond breakage, known as what? Cleavage. We can also what? Bond cleavage. So we use this sign for bond cleavage. So now, to cleave this molecule, we use this. So we can see here we have A and B being cleaved, that is being disconnected or being broken. Now this is to show that A and B are what? Disconnected. So whenever you see these signs, so it shows that is bond has been what? Broken. So then to form, we can see this is a retrosynthetic reaction. We have AB in a retrosynthetic being turning to what? A two distinct elements. That is, this is like, so for example, this is a target molecule. It's a target molecule then being broken to their precursor. So that is, for every retrosynthesis reaction, we disconnect molecules, we disconnect complex molecules, and we don't just break. There is this branch of chemistry called spectroscopy, where I think is infrared. When we know the possible, So under this branch of spectroscopy, like likes of NMR, nuclear magnetic resonance spectroscopy, the infrared spectroscopy. Now we have HNMR, we have CNMR, and this kind of spectroscopy we also deal with cleavage also. That is, so now in this scenario where for a retrosynthesis, the main thing is that to separate bigger or complex what molecules. And this connection, you don't just break bonds, you don't just what break bonds. Like, let's use for example in spectroscopy where we talk about we have different kinds of hydrogen. We have for example H, 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 H. So now this one have a single environment. This benzene has a what? A single environment. That is, if you should cleave by the left, cleave by the right, all the hydrogen here represent what? A single environment. So in disconnection, in retrosynthesis, you don't just disconnect, you disconnect based on some certain principles, based on the reagent you are using. So now for example we have acetaminophen here, that is Tylenol. So now we want to cleave, that is we want to know this is our starting material, that is we want to know what form acetaminophen. So the first thing is here is to disconnect, that is cleave. And we don't just disconnect, we don't disconnect this, we don't just disconnect this. So that is where our radio selectivity comes in place. Our radio selectivity comes in place, where we select a particular area to disconnect first. So now to disconnect, we disconnect the ketone group out. We cut out the ketone group. So this is the ketone group. We cut it out. We are left with the amine group. So we are left with aminophenol. So we are left with the amine group. So after disconnection, we are left with the amine group and and the ketone group. So we can see this is the starting material. So we can call this para-amine phenol. So when we talk about para in naming organic compound in advanced level, we don't make use of 1 kinikon, 1, 2, 3 kinikon, dikinikon. We make use of what we call the auto, the meta, and the para. That is auto position, the meta position, and the para position. So we call this one para-amine phenol because you can see amine is in position, that is in angle with the phenol, is in angle with the OH group. And if the OH is said to be in this position, they are said to be in auto position. And even the OH is said to be in this position to have been the meta position, but they are facing each other. So this is the para position. So after proper disconnection, that is disconnecting the ketone group from the amine group, we are left with this, and we have our ketone group here. So either you have this or you have or you have this. This is what we call acid anhydride. This is an acid anhydride. So we can successfully see that this is our target molecule, and we've successfully gotten our precursor. So this is the first precursor A, and this is the second precursor. We can see that A and B react together to give us this acetaminophen, otherwise known as Tylenol. So the main thing of retrosynthesis is that we talk about the first step, which is the retrosynthesis arrow. This is the arrow. We represent it with what? With an arrow, which is the first thing. That is to signify what kind of reaction we are dealing with. So the next thing, what do we do in the next step? We what? We disconnect. That is, we cleave, we break bonds. So at this position, we can see that if cleaving our what? If cleave, we break bonds. So when we cleave bonds, we got our what? Our precursor A and what? B. We've gotten our what? Precursor A and what? And B. Sometimes disconnection of the bond does not lead to the logical starting material. That is, when we disconnect bonds, unlike acetaminophen we did, that we got our starting material. In some scenario, that one is, you can say that one reaction is said to be just straightforward. But from some reactions, when you disconnect, you don't directly get the starting material. In that situation, when you don't get your starting material, one functional group is replaced by another to make the disconnection possible. That is, in a situation, for example, the acetaminophen we did earlier, where we talk about NH2, where we simply disconnect and we get our subsequent group. What our subsequent what? Group. Like this. So now, there's some scenario that if you just disconnect, you won't get the original starting material. So in cases like this, there's what we call functional group conversion. That is, one functional group is replaced with another what? Functional group before you can successfully disconnect. So in short, we call it what? FGI. That is, for example, let's consider this reaction. Let's consider this reaction. This reaction, we can't just leave or disconnect this from the benzene ring and get the reaction is said to be wrong. The reaction is said to be what? To be wrong in this manner. That is, this in this case, this connection is not favored. There's what we call functional group what? Interconversion. That is, before you disconnect, the first thing you do is that you replace this functional group, this ketone group is replaced with what? OH, alkoxy group, before you can successfully disconnect. So now, for this reaction, acetophenone, when we talk about acetone in the first place, acetone means propanone. So now, the structure combined together here, we have what called what? Acetophenone. So the first instance, when we talk about functional group interconversion, FGI, that is, look at this point, we don't just disconnect to give us, like doing rule to the answer and giving us our end product. No, there are some conditions that you don't just disconnect. You need to what? In the place where disconnection is not working, you need to change functional group before you can eventually or successfully what? Disconnect. So in this scenario of acetophenone, the first we can see here, when we try to cleave, we got this. We can't say truly we are meant to get benzene as a distinct, one of our precursor, and get acetone also as our precursor. but this route with which we pass to get our end product is said to be what? Wrong. It's said to be what? Wrong. But the correct route we need to pass is this place, is this point which we call FGI. That is, we need to, before we cleave anything here, we need to what? Replace the functional group with another before this connection can be successfully. Because when we consider carbanions, that is carbanions, we have different kinds of reactions, like the likes of Hadot condensation, the cross Hadot condensation, the cleansing condensation, the Michael reaction, the Robinson annulation reaction. There is always always a point where we attack the alpha carbon and we convert ketone to another group, where we attack the alpha carbon and we convert the ketone to another group. So if you have understanding of carbanions and carbocations, you should know the reason why we need to disconnect first. Because in carbanions, there is no way you will get ketone in this format. There is no way you get what your acetophenone in this, with this two starting material. There is no way you just do the root to the answer and get this. There's what we call what? There's what we call deprotonation of the alpha carbon. So that is, the first thing we did is that we dip. So in the what we mean by alpha carbon is that, for instance, we are naming with 1, 2, 3, 4 in our basic chemistry, and I also said we can also name with what? The auto, the meta, and the what? And the para. But in another case, we can also name it what? Alpha, beta, and gamma in advanced chemistry. So now in carbanions, the way we name is we make use of alpha, beta, and the what? And gamma. So now any disconnection, so in order to form carbanions, we first what? Deprotonate the what? Alpha carbons. We deprotonate the what? Alpha what? Carbons, to form our negatively charged what? Ions. That is carbon with a negative what? Charge. With a negative what? Charge. So now the alpha carbon is being at, so in normal carbanions, the Hadots and our cross Hadot condensation reaction, we should know that the idea is from that we attack the ketone to give us what? Alcohol first before we can get this. So that it is a very long series of process before we can get this, and eventually what? End here. So now we can see, first of all, we can't just disconnect straight to give us this. That's the wrong line. Even that's why I said, for electrosynthesis, the first thing you need to learn is what? Learn the forward reaction first before you can think of the backward reaction. Because you can never think of the what? Backward what? Reaction. Learn the forward reaction first. At the beginning, you have a deep understanding of what? The forward reaction, the way in the manner with which we got this. So the backward reaction will what? Won't be very difficult. So now I advise you to learn, first of all, learn the forward reaction. So with the forward reaction, you will definitely know that in the formation of this, there have once been an hydroxy group in the process of formation of this. That is an hydroxy group. We once has an hydroxy group in formation of acetophenone. With that, you just, so you can see now, we didn't just cleave for this one. We didn't just what? Cleave. We interchange the functional group. So we can see we have our OH group. So through the reaction mechanism in Hadot condensation and cross Hadot condensation, there have been elimination of the pi bond, and we've added H hydrogen to form hydroxy. Then we can further break down. We see we ended up having our benzene ring and our acetone, and we have our what? our acetone, that is propan-2-one. So in the case of FGI, you need to denote first. What do you mean by denotion? Na in this scenario, in your retrosynthesis arrow, you place it, you put FGI what in front on top of the arrow, that is to indicate you've successfully convert one functional group to what another functional group. That is successfully what convert one functional group to what another functional group. So we said we've convert from ketone to what hydroxy to hydroxy. So you place it on the arrow, that is FGI. So you can see this is retrosynthesis is one of the most simplest part of chemistry. You don't need the reagent. You can see you didn't specify the reagent we use, though you should know the reagent we use in the conversion. You didn't specify the what the reagent, you just indicate FGI, that is they are being swapped of what functional group. So I would advise to go and learn carbocations and carbanions. I think I will send some slide on carbanions and carbocations. It's also one of the most concrete parts, that is to understand the retrosynthetic force. You need to know some your basic knowledge in chemistry during your undergraduate. Pause. So we can see we indicate FGI here, but in this scenario we didn't indicate FGI. That is, there is no conversion of functional group. So no FGI here, but we have FGI here. That is, this is to show that we didn't interchange functional group, we just cleave straight. But here we didn't just cleave. First of all, we what interchange the functional group. Then after the interchanging of the functional group, we later what cleaved. And another thing is that we didn't just cleave. We have some conditions where some people can cleave from here, another person can cleave from here, another person can cleave from here. So you don't just cleave. That is where radio selectivity comes in. So radio selectivity will pinpoint where you should cleave. That if I should cleave from here, the product that I will get, will it be a reasonable product? Or if I should cleave from here, the product I will get, will it be a reasonable product? But if I should cleave from here, this is one of the most perfect points with which you can cleave, which will give you your starting material. So this acetone, you can see we got acetone, and even if you cleave from here, you will never get acetone, because in adduct and cross-adduct condensation, this is the right product to use. That is, this one has a what alpha carbon. We can see the acetone, there is a presence of alpha carbon here, which you can easily deprotonate. If you have cleaved from here, and we can just have CH3 plus OH and the benzene ring. How do you end up forming this? That is, does it correlate at all? So that is, radio selectivity comes in place in the room of what disconnection. So as we said earlier, we didn't indicate FGI here because we just disconnect. But at this point, we indicate FGI, that is to show that there have been replacement of one functional group with what another. Do we get? So we're going to be showing you some examples of functional group interconversion. That is where in the case where disconnection is not possible, what we do before we disconnect is that we convert from one functional group to what another functional group. So now, as you all said, for example, this is our usual sign. So you indicate FGI on top of your retrosynthetic arrow. So the first one, this is an aromatic compound, and if you know why we are, if you don't write benzene in this manner, if you can't write benzene in this manner, you can also write it in this manner. That is, um there's in benzene there's what called shifting of pi bonds. When I go calculate, there's what called shifting of pi bonds. That is, there are 6 pi electrons. We can also put it in this manner instead of writing the pi. So now we have aniline, which is NH2. We have an aromatic. This is an example of aromatic compound. This is called aniline. So then, that is, we are going to find the retrosynthesis of this reaction. To find the what retrosynthesis of what this reaction, we can't just break down and get this and get this. This is wrong. It's going to be what very what wrong. The first step is what, you can't just cleave. You don't just cleave and get this. So the first thing we need to do is what, apply the rules of what FGI. So we need to apply the rules of what FG. We can see FGI. No reagent is added. So FGI has, so no reagent is added here. So you should know the specific, in case where the reagent is being asked. That is, during your functional group interconversion, indicate the reagent being used. You should be able to what, give account of your reagent. So now, that is, we need to convert this amine group. You need to convert this amine group before we can have a thought of disconnection. So then, this is our retrosynthetic group, and FGI means you want to convert, you want to change the functional group. So we end up getting this. We can see this is a nitro compound, an aromatic nitro compound. If successfully convert from NH2 from a amine to what, a nitro what compound. So this is to show that the functional group has been what, interchanged. It has been what, interchanged. So then you can successfully what, break down according to Fidecraft alkylation and Fidecraft acylation. So in Fidecraft, where we make use of acid catalyst, where we make use of a Lewis base and a acid catalyst like iron bromide to where we call in nitration. If you want to form an amine, so we introduce a transition element catalyst like FeBr2. So to get this amine, so that it, the reagent matters. If you had a deep understanding about reagent, it will be very difficult in understanding retrosynthesis. So the main part is that understand your basic chemistry. So so these are other examples of functional group interconversion. You can see this one. This is an amide group. You can see an amide group attached to our aromatic compound. So we can't just disconnect. So we can interchange the functional group by replacing with FGI. So we can see after successfully conversion, we ended up having our cyanide, that is from amide to what, to our what, cyanide attached to the aromatic compound. We can call this our benzene. So we can see we ended up having what, cyanide attached to what, our benzene. So while after the successful replacement of a functional group, so at this point also we have our amine. This is the amine part, which is the functional group, and this is what, the alkyl part. We can see AR, this is the alkyl part. So now we don't just convert, we can see on our retrosynthesis aldo there's FG, that is functional group interconversion. So when we convert from this NH2, we got our what? Our nitrile compound. This is nitrile. That is, when we talk about nitrile, an alkyl with triple bond attached to what? Nitrogen. So we're talking about symptoms and synthetic equivalent. I think in the past question you sent, there's a point where we are being asked that define symptoms and define what? Synthetic equivalent and define FGI. So now when you talk about symptoms, you should have your quick backgrounds on free radicals. When you talk about how we generate what? Radicals, it is also, both of them are also what? In relations. When we talk about radicals, so now assignment, what is the difference between radicals and symptoms? What's the difference between what? Radicals and what? And symptoms. So now, symptoms are the idealized fragment results from the disconnection. Idealized what? Fragment result from what? Disconnection. So now when we talk about symptoms, so we talk about fragment result from the breaking down of what? C to C carbon, or C to H carbon, or C to what? S carbon. So then when we talk about C to C carbon, you should know what it means. When you talk about C to H carbon, you should know what it means. But when we talk about C to S carbon, the X here can be represented as halogens. That is carbon bonded to halogens, and this one is what? Carbon bonded to what? Hydrogen, and this one is what? Carbon bonded to what? Carbon. So now when we talk about symptoms, symptom means the disconnections into smaller fragments. And another condition for symptom is that during the process of what? Of symptoms, there is always formation of the what? A positive and the what? A negative charge. As when you disconnect carbon, the carbon always carry a positive charge and the what? And a negative what? Charge. For example, if you are to disconnect this carbon, maybe you are to disconnect this compound C to what? O. That's what we can see. This is an example. C2 is an example of CX. So we can have, in this connection, we can have C positive plus what? O what? Negative. So when we talk about this connection, that's the one of the scenario. Then carries charge. So symptoms is like breaking down to a what? A smaller fragment, and each fragment carries a designated charge. So unlike homolytic and heterolytic cleavage, when you cleave bond, they both has radicals. Like for example, when we talk about BH4, when there is a cleavage, we talk about this is BH4. So when there is a cleavage, so we ended up having B, H, and H. So that is both the bond here has more successfully been break. So we have radicals. So we have BH3 and H. But in the case of symptoms, when we cleave into smaller fragments, we ended up having what? Positive charge and negative charge on tops of the what? Compound. So to furthermore our example, assuming we have C to C carbon, you ended up forming what? C plus or C minus as our respective charge, or we have C to H, we will definitely end up having C plus, C minus, or H plus. Or we have C to X, we will definitely have what? C plus and what? X what? Minus. So this is the phenomenon of what? Of symptoms, that is breaking into smaller fragments, and each fragment has a what? it carries a charge, and each fragment carries a what? A charge. So now the next one we talk about synthetic equivalent, that is the equivalent of the what? Of the symptoms when reagents are being added to it. Pause. This is when we talk about synthetic equivalent. Synthetic equivalent can be referred to as reagents, that is actual compound that are equivalent to symptoms, that is compound that are equivalent, that we can compare to what? To symptoms, that is fragments. So now another one is they act as a source for the symptoms. So they act as a source, that they are a pathway for the what? Symptom. So we'll show some simple example below to differentiate what we meant by symptoms and what? Synthetic equivalent. That is, our synthetic equivalent a pathway to symptoms.